Hello, my name is Ben Fry, and I'm a graduate student in the Ultrasound Imaging and Instrumentation Lab at Stanford University. Today, we're going to be presenting on differentiable beamforming for distributed attenuation estimation and spatial gain compensation, SGC. When looking at medical ultrasound imaging for sound speed and attenuation estimation, there's different motivations for attenuation estimation. Attenuation estimation can be used as a diagnostic biomarker, such as in this plot we see on our horizontal axis steatosis grade, and on our vertical axis we see fat content percentage. In this case, these quantities were determined using sound speed estimation, but we could imagine how attenuation could be used as a complementary biomarker for differentiating steatosis grades 2 and 3, especially at these higher fat content percentages in a multi-parametric model where sound speed and attenuation are used together. We can also use attenuation estimation. In this work, we present image correction with spatial gain compensation, or SGC. And the idea of SGC is that we have some attenuation estimation that's in a distributed manner. So in a field of view, we have a localized attenuation estimation, and we can use this attenuation estimation to compensate a beam mode iteratively. In this iterative process, we can see that this attenuating inclusion shown in this region produces a shadow initially in the beam mode, and through this iterative process, when attenuation is better estimated, the shadow is removed in the compensated beam mode. Some of the limitations of existing attenuation estimation models are that they require reference measurements, that they're based on layered media assumptions, or that they have low resolution for distributed estimations. And this is due to the fact that these models typically look at regions of interest of 10 to 20 wavelengths axially and laterally. And using these spectral-based methods, they're trying to determine an attenuation coefficient slope by doing some frequency analysis. This frequency analysis requires a region of interest, like I mentioned, about 10 to 20 wavelengths, and this lowers your ability to do distributed attenuation estimation. Now looking at our differentiable beamforming model, differentiable beamforming enables parameters such as timing delays, apodization, and attenuation estimation to be iteratively improved by optimizing an image quality criterion through an automatic differentiation framework. So I'll go through the process of how this works for attenuation estimation. First, we start with the initial estimate of attenuation. In this field of view, for example, we have an initial estimate of 0.5 dB per centimeter per megahertz. We then reconstruct synthetic subaperture pairs. In this subaperture image envelope represented by S sub A at a position X at a certain frequency F, we have this first term, which is the unattenuated image envelope. This represents the ideal image envelope that has no attenuation. This is the compensated image envelope that we're trying to create. And then this term represents the components of the segments along a ray trajectory. So this ray trajectory goes from our transmit aperture down to the point X, and then to our receive aperture. Along this ray path, we have multiple segments that we break into, and we can calculate the accumulated attenuation along this ray path by doing some integration. Once we have reconstructed our synthetic subaperture pairs, we compute loss on kerneled patches represented by these red dots here. This is our loss function that we're looking at. So we're comparing subaperture pairs SA and SB, or more specifically, the logs of these subaperture image envelopes. And we're looking at subaperture image pairs that are constituted by common midpoints. So we have a group of subapertures that all share common midpoint, and we're looking at the difference between these two, which simplifies to a ratio of the observed signal SA and SB and the components that make up the segments. We then finally backpropagate our errors through our image reconstruction model to update the original attenuation estimation. So we backpropagate this loss from the loss step through the delay and sum image reconstruction to the initial attenuation estimation. Now this produces a referenceless model for attenuation estimation. And in order to make this model work, we have to consider a couple different sources of energy loss. The first source of energy loss is what we're estimating, or this concept of attenuation through absorption. So when I refer to attenuation estimation, we're referring to attenuation through physical absorption, which follows this exponential decay power law. We also have to consider geometrical spreading, which is energy loss due to spreading of the signal over space, and transducer directivity. So physical transducers have these different directivity patterns. Sometimes geometrical spreading can be included in the transducer directivity pattern, but they have these special or unique directivity patterns. The final contribution is impedance mismatch. So this is attenuation due to specular reflection. Currently in our model, we integrate terms A, B, and C, and we don't consider this term D. To test our model, we started by creating heterogeneous K-wave phantom simulations, which is inspired by this work from IUS in 2022 called Towards Attenuation Imaging with Computed Ultrasound Tomography in Echo Mode, CUTE, which was an extension of the CUTE model for sound speed estimation. So there's 5 different phantom layouts in this proceeding. The first phantom, or all 5 phantoms, had the same background attenuation of 0.5 dB per centimeter per megahertz. This first phantom had a positive attenuation contrast in the inclusion, meaning that the inclusion had attenuation greater than the background. The second phantom had attenuation lower than the background. And the third, again, had a positive attenuation contrast, just with a smaller inclusion. Phantoms 4 and 5 had uniform attenuation, but a different echogenicity for the inclusion. Phantom 4 had a hypoechoic echogenicity, and Phantom 5 had a hyperechoic inclusion. Next, we ran these phantom layouts through the acoustic simulation toolbox K-Wave to produce our channel data cube. Using a full synthetic aperture, we were able to produce our channel data cube, which is our transmit events by our receive events by our samples in time. And then we used a conventional delay and sum beamformer to produce a beam mode to make sure that we were able to beamform the data. And in this case, this is the hypoechoic inclusion example for Phantom 4. We then went ahead and tested our model on these different simulation data results, and we produced the model results for Phantom 1 and 2 shown here. In the first column, we have the B mode that is iteratively compensated. In the second column, we have our attenuation estimate. And in our third column, we have the mean absolute error, which is the attenuation estimate minus the ground truth. We can see that these blue patches here represent where our loss is taken from in the image space, and that our model is able to estimate this inclusion here, or the positive contrast attenuating inclusion. We see that over time, or over iterations, our model mean absolute error starts to converge to all white, which represents a 0 error, or 0 mean absolute error. Additionally, our standard deviation in this distributed estimator drops over iterations. So that means that we reach a lower standard deviation across all of our image space. We can see for the second phantom, our model is able to estimate the negative attenuation contrast as well. And from these 2 phantoms, we see that the model is sensitive to initialization and attenuation contrast polarity. And by attenuation contrast polarity, I mean that in the case of Phantom 1, where we had a positive contrast attenuator, our model was able to reach a lower standard deviation in the mean absolute error than in the case of the negative contrast polarity. Looking at Phantom 3, which was the smaller inclusion, we can see that the model resolves the inclusion in this case. So the model is able to detect small attenuation inclusions in this simulation data in this configuration. Because the model is not a spectral-based method that relies on region of interest windowing, it offers the potential for highly distributed attenuation estimation. So this is one of the potential advantages of this method over existing methods that require or spectral-based methods that require regions of interest is that our model doesn't require this. Phantoms 4 and 5 were the uniform attenuation examples. Phantom 4 was the hyper-echoic inclusion, which we can see here. We can see that our model was not impeded by this hyperechoic inclusion or this change in echogenicity, and it is able to estimate this uniform attenuation distribution. Despite echoic inclusion variation, the model has convergence stability in this simulation data. Here's a summarized table of our model results on simulation phantoms. Here we can see phantoms 1 through 5, which we just looked at on the previous slides. And in this column, we can see the mean absolute distributed error in units of milledecibel per centimeter per megahertz. We also see additional homogeneous phantoms of attenuating values 0.7 through no attenuation. I'd like to point out that our model was initialized with the background attenuation value for phantoms 1 through 5, which is one of the reasons why the mean absolute error is lower than the case for the uniform attenuating phantoms. But we do see very low standard deviation in our error maps across all the different phantoms that we looked at in simulation. Next, looking at experimental data acquisition from an attenuation phantom, we had 3 different experimental setups. The first is the case where we have attenuating inclusions. So the background's value has a value of 0.7 dB per centimeter per megahertz, and the inclusions have a value of 0.5 dB per centimeter per megahertz here. The second case was where we had a bilayer phantom. So the top is 0.7 dB per centimeter per megahertz, and the bottom is 0.5 dB per centimeter per megahertz. So everything below this line has 0.5. We can see the experimental setup here. We have the probe looking across this division, and the division represents 0.7 on the left and 0.5 on the right. The third setup was a bipartition. So now we have the probe straddling this boundary line. So everything on the left is 0.5 dB per centimeter per megahertz, and everything on the right is 0.7. So in total, we used 3 experimental configurations and a full synthetic aperture FSA transmit sequence were used to capture data from a CRS 040 GSC attenuation phantom. We did this using a Verisonics L12-3V transducer and a Verisonics Vantage 256 system. Here are model results for experimental heterogeneous attenuation phantom data. The first case where we had the attenuating inclusions that were negative attenuation contrast, so they're lower than the background. We could see that our model did not recognize the difference in the distributed attenuation for the inclusions. In the case of the bilayer, where the top was 0.7 and the bottom was 0.5, we saw that over 100 or over 60 iterations that the model estimated higher attenuation in the top than in the bottom, but we still didn't see this clear boundary at roughly 27 millimeters. And in the third case where we had the bipartition, we could see that our model was able to estimate this lateral variation in attenuation and iteratively improve this compensated B mode through spatial gain compensation by brightening the right-hand side of the image. So due to spatial bias in the forward model, the model only detects lateral attenuation variation in experimental data. Spatial gain compensation, or SGC, which we're introducing in this work, enables brightening of the attenuated bipartition B mode image. In summary, the model is sensitive to initialization and attenuation contrast polarity. Because the model is not a spectral-based method that relies on region of interest windowing, it offers the potential for highly distributed attenuation estimation. Despite echoic inclusion variation, the model has convergence stability in simulation data. Due to spatial bias in the forward model, the model only detects lateral attenuation variation in experimental data. For the acknowledgements, I would like to thank the members of the Ultrasound Imaging and Instrumentation Lab led by Jeremy Dahl for guidance on this project. Thank you for your time. Do you have any questions?